So based on the domain of discourse, okay, we can evaluate the truth value of a predicate logic statement. Okay, so if, for example, in this example, which is P is such that X is an integer greater than 2, okay? If I tell you that X belongs to the set of positive integers, okay? The set of positive integers, right? Then in evaluating this statement, you realize that there is a certain X value which will be positive 1, okay? Positive 1, which will make the statement invalid or false. If we are saying that X belongs to the set of integers, of positive integers, okay? Positive integers starting from where? From 1 to positive infinity, okay? To positive infinity means that we have some values of X which are not greater than what? 2. So for example, 1 and 2, okay, will make the statement false. So given the domain of discourse, we can evaluate the truth value of a given statement to be true or to be false. Very good. Now let's go down a bit. Okay, I think I've explained the definition 6.1 already. Okay, so we want to look at further examples. So he says that another example will be the statement P, which is a function of n and is defined as n squared plus 2n is an odd number. And the domain of discourse for n has been defined as what? Has been defined as n belonging to positive integers. So if that is the case, then it means that n could be 1, 2, 3, etc. Okay, good. Now, if we pick the first value of n, which is 1, into this statement, 1 squared plus 2 times 1 will be 2. 1 squared is 1, so 1 plus 2 will be 3. So 3 is an odd number. The statement will be true. Now, if we pick the next value of n, which is 2, 2 squared plus 2 times 2, 2 times 2 will be 4. Okay, so we have 4 plus 4 will be equal to 8. 8 is not an odd number. Okay, does not belong to the odd number set. Okay, so for these given values, which are even numbers, P of n is not going to be what? True. Okay, this is what we are saying. So for certain values of n, this statement is not what? Is not true. But for other values, the statement remains true. Now, in predicate logic, there are two main types of quantifiers which we use in evaluation. These are the universal quantifier and the existential quantifier. So universal means In short, we say for all, okay? So universal for all. For all, okay? Or you can say for every value. For every value, okay? Whereas the existential, we are saying there exists some, or for some, for some could be even a single value, okay, for some. Or you can say there is existential, there is for some, okay, good. Now let's go down a bit. So there are more notes to explain this, but key thing we have to take note is the expression, how to write the expression for the universal and the existential quantifier. Okay, we usually write the statement like this. So this will be interpreted as for all x, the statement p of x. Okay, so that means I've already written my statement p of x. Okay, so for all x, p of x. We could also write it this way: for all x, p of x. This and p of x, okay, is the same as what we have here. Then sometimes we can also want to bring the, aside writing the statement, we want to indicate the domain of x. Okay, the domain of x within the statement. So that's the domain of discourse. So we say for all x belonging to the set of natural numbers, then the statement follows. Okay, and then sometimes there is restriction to on the domain of x. So that too will want to indicate that. Okay, so you write it as what? For all x belonging to natural numbers such that x is greater than what or equal to 0. Then the statement p of x. Okay, good. We'll take some examples as we go down. Good. Now let's look at the notation for okay. So, okay, we have an example here we want to look at. Okay. So we're saying, for example, if we define q of x to be x plus 1 is less than what? 4. X plus 1 is less than 4. And then let's say that our x has been defined on what? The set of, let's say, natural numbers, okay, on the set of natural numbers, okay? Good. In this analysis, if first, let's look at how to write the statement. So we would have written, like we said, one way of doing this is what? For all x, okay, for all x, right? P of x, sorry, q of what? Q of x, because we've already defined q of x, okay? For all x, q of x, okay, good. Now, so writing this, we already know natural numbers are what? Are greater than what? Are greater than 0, okay, good. Now, let's do this analysis. So if we're dealing with natural numbers here, then we can take x to be 1, 2, 3, and so on. and so forth. So if we take 1 here, 1 plus 1, okay, that would be 1 plus 1, sorry, 1 plus 1 will be equal to 2, right? Will be equal to 2, and 2 is less than what? It's less than 4. Okay, similarly, if we take 2, it will be 2 plus 1, which will be 3, which is less than 4. But when we take x to be 3, 3 plus 1 will be 4. Okay, 4 is not less than 4. Okay, which means that if we pick any value above 3, the statement will have a false value. Okay, if we pick any value above 3, x above 3, the statement will have a false value. Okay, very good. Else, if it is 1 and 2, it will be true. But if the values of x are 3 upwards, 3, 4, 5, they will all be false. Okay, but the very fact that we've written the statement like this, that for all x, x plus 1 is less than 4. For all x, you've already concluded that for all given values of x in the natural number, the statement x plus 1 is less than 4. Okay, and we are realizing that there are some of the x values which makes the statement false. Then the whole statement is going to be what? False. Okay, so we say that the true value of this given statement, which is for all x, q of x, is going to be what? Is going to be false. Okay, so that is how we do the evaluation. Now, any question here before I proceed? Any question here?
No, sir.
Okay. Now, let's move on. Okay. There's another question there. We are saying for all real x belonging to real numbers, x squared is greater than or equal to 0. Of course, real numbers consist of negative values, rational, irrational, okay? Yeah, and if you square a negative number, you still get positive, okay, which will be greater than 0. And if the real number is 0 and you square it, you still get 0. So it will be equal to what? 0. So this statement will be true because for every real number you pick, the square of the real number will be greater than what? Will be greater than 0, okay? If you pick any real number and you square it, it will be greater than 0. So the statement here has a truth result. Then we move on to the existential quantifier. Existential quantifier, okay, says that there is a value, okay, in the domain of discourse. There exists a value, or there is some value in the domain of discourse, okay, for which the statement is what? True, right? And like you saw from the beginning, here instead of for all, we have there exists. So there exists x such that the statement P of x. So we can write it together with the domain and then the limitation of the domain. They are the same. Okay, let's do some evaluation based on the existential. So I think we are taking the same previous example. Okay, so if we're still looking at the set of integers like we said, right, and we write there exists an X such that Q of X is true. Okay, good. Now, because we said X belongs to integers, I think we use natural numbers. X belongs to natural numbers. Okay, if we pick 1, 1 plus 1 will be 2. 1 plus 1 will be equal to 2, which is true. Okay, it's less than 4. If we pick X to be 2, 2 plus 1 is 3, right? But when we pick the value 3 plus 1, 4 is not less than what? 4, okay? 4. And then when we take X to be 4, it will not be less than 4. So, you see, above the value 3, the statement is not true. But because we have written there is some, we are only saying there is a certain value in this domain. So let me write out the domain in terms of figures. That's 1, 2, 3, and so on. Okay, we are saying that there is some. So as long as 1 and 2, even if you have just one value satisfying the condition, then indeed there is a certain X in the domain which satisfies the condition. So once 1 and 2 satisfy the condition, then we say that the statement has a true value. Why? Because there are indeed some X values for which the statement X plus 1 is less than 4. Okay? Yeah, that is the difference between the for all. For all means everything has to satisfy it. But for some, or there exists, we only need just one to satisfy. And if one, element within the domain of discourse satisfies the condition, then we have a true statement. Okay. We have another statement here. He says, another example here. There exists a Y, okay, giving the statement Y plus 2 is equals to Y. Okay. Yeah, now if we take natural numbers, this will never hold. Because if you take Y to be 1, then 1 plus 2 will be 3. 1 plus 2 will never be equal to 1. Okay. Regardless of the natural number you pick. If you pick natural number to be 10, 10 plus 2 will be 12. It will not be equal to 10. So this statement is straight away going to be what? False. You understand? So there is no value. There is no natural number which will satisfy this condition. In fact, there will be no real number which will also satisfy this condition. So we say that the given statement, there exists Y, said that Y plus 2 is equal to Y, is false. Okay. Now, finally, we have combining quantifiers, which we use a lot in programming, okay? Because we have a number of statements which we program. So you not just be programming using single statement like that. So we have a statement like, yeah, here we have a combined statement. Okay. So for all X, there exists a Y, so that the statement X plus 2 is equals to what? Is equals to Y. Okay. So that this is equal to Y. Yeah. Let's give it a try. So first we need to define the domain of discourse. So we can say that X and Y, okay, X and Y both belongs to natural numbers, okay. If that is the case, then it means our x will start from 1. So we have x, 1, 2, 3, and so on. Y will also be same. Okay, 1, 2, 3, and so on. Okay. Yeah. So per our statement, x plus 2 is equals to y, and we are told for all x. So if I pick any given value of x, there should be a certain y such that, okay, x plus 2 will be equal to y. Let's see if this is true. So if I pick the value x equals to 1, then I'm going to have 1 plus 2, okay? 1 plus 2 will be what? 3, not so. And then the statement says, once I've picked x, there should exist a certain y, also in the natural number, okay, which will be equal to x plus 2, okay? So x plus 2 is 3, and indeed, 3 is a natural number, and that's the value of y. Okay, so 3 exists in natural numbers, or y exists in the set of natural numbers to make this true. If I pick x to be 2, then I'm going to have 2 plus 2, which is 4. Okay, 4 is also a natural number, so there will surely exist y, which is 4, okay, belonging to the set of natural numbers. So clearly we can see that if we select any x value, there is going to be a certain y value, okay, which will, indirectly will, is 2 more of what? Of x, let me put it that way. The y value is 2 more of the x value. Okay, so that is going to surely exist. Good. Looking at our last example before we wrap up will be the statement x squared is less than y squared, implies that x is less than y. Okay, let's see. This is p of xy, okay? And then we've been told that for all x and for all y, the statement, okay, x squared less than y squared implies x is less than y. Once again, we need a domain of discourse, so I'm going to still maintain my set of natural numbers. Sorry, this should be set of natural numbers. Okay, so if we do so, then when I pick any x value within natural numbers and square it, okay, and I do same for the y, then this statement must hold. That's what they are saying. So let me take x to be 2, okay, and then let me take y to be 3. So if x is equal to 2 and y is equal to 3, then 2 squared will be what? Less than what? 3 squared, which will also imply that 2 is less than what? It's less than 3, which is true. Okay, so as far as the square of x is less than the square of y, then 2 will be less than y. Okay, however, if I change the domain of discourse and make it let's change the domain of discourse to be X, Y belongs to integers. Okay, integers mean we have both negative and positive values, whole numbers. Okay, good. So if I should pick X to be, let me say -1, and I pick Y to be -2, okay? Then the square of -1 will be less than the square of -2, okay? Will be less than the square of -2, okay? But that will not imply that -1 is less than -2, okay? This portion is going to be what? Is going to be false, okay? Even though this side is true, okay, this side is going to be what? False, which means that we are moving from a truth to what? A false statement, okay, which will make the whole statement to be what? To be false, okay? So depending on the domain of discourse, the conclusion changes. Okay, so you take note of that. There are more examples in there. Some are converting the logical statement, okay, logical expression into English statement, and vice versa. So you take note of that. Those examples. I'll send